Good morning. Welcome to the Elixir Friday Coffee. Today we have Karel Berka from University of Palacký, Olomouc, and Karel is creator and also the contributing member to the first known molecules on membranes, and he will be giving you a short summary how that database is working and what you can get from it. So Karel, floor is yours. Please start. Karel, you are muted.
Welcome to the Friday Coffee, where I will be speaking about the MolMeDB, which is our database about the small molecules of membranes, which we are developing here at Palacký University. So the question is, why to bother with molecules of membranes? And the major reason why to bother with them is that the molecules actually interact a lot with the membranes, and majority of the targets for molecules are actually on the membrane or behind the membrane inside the cell. So that means that if we want to understand the pharmacology of how the molecules can interact with the cell, therefore we need to look into the permeation and accumulation properties. And for the permeation, the membrane actually acts as a barrier. So most of ions and polar compounds basically are impermeable, and therefore they need some transporters. But the drugs are usually amphipathic, so they can go by themselves by passive permeation, or they sometimes can use also some kind of transporter as well. So there is plenty of different drugs, there is plenty of different compounds, and as such, we wanted to know how to describe this. And for a long time, there is plenty of descriptors about these compound membrane interactions, like the penetration coefficients, partition coefficients. There is multiple levels about how to describe those things. Even from the molecular dynamic simulations, you can get the free energy profile of how the molecule actually pass through the membrane. And of course, there is plenty of data also on substrates and inhibitors of transporter. But the major problem for us when we started with this was that the typical interaction data representation in the literature is such like this. So basically a picture or graph inside the paper, or if you are a little bit more lucky, the table, which is in PDF format and therefore really hard to access the data and to work with them. So if you are lucky, you can get the data from supplementary information in the form of a table. And if you are really lucky, you can get some data also from bioassays downloadable from the PubChem or Campbell or something. But most of these data actually were not machine readable and comparable to each other. So in order to do the study for comparison to the experimental values, we had to go through the literature looking for the compounds which we were interested in, and we've left quite a lot of compounds behind because those compounds which we've seen did not have any identifiers on them. So it was really hard to compare data. So for this reason, we started to integrate everything into one resource. And that resource we called MolMeDB, Molecules on Membrane Database. And here we combine the data from articles, experiment, and our own calculations to generate the database that will provide those data in a similar manner and comparable manner for each compounds and experiment. So what do we have? We have a database where we have the interactions stored for molecules from experiments, simulations, and also now for the transporters as well. So let's have a look. This is the web page. This is the home page of our database. It can be found at molmedb.upol.cz. And here what you can do is either, you can browse. For instance, I can browse the membranes. And here is a navigator that guides you into a type of membrane you want to study. So for instance, here the OPC, and the description of the membrane. And here you can see, you can compare these compounds in together in our tool, which is called Comparator. In Comparator, you can basically compare any data which we have stored, but you can also download the data to work on them on your desktop. Here we have plenty of different methods, we have plenty of different membranes, and this is just a selection of compounds for which I've plotted the graph for free energies. So this is all these different xanthines, so the compounds such as caffeine and its metabolites. And if I compare that, I can see that the caffeine actually is one of the most permeating molecule here, because the free energy profile shown here shows me here the around the zero. This is the center of the membrane, and this and here is the part which is in the water phase. So I can look into how the molecule will cross the barriers energetically by going through the membrane according to the height of this barrier. So I can say that the caffeine itself is able to cross, but its metabolites won't such easily. So this is the comparator and what we have stored for individual compounds. So we can, instead of membranes, we can go into the search, where you can search either by membrane again, or by methods, or by smiles, name, and also these days also according to the transporters for which we have the data. And caffeine as a typical drug, we have the first part. This is basically a description about the molecule, how it looks like, 2D and 3D picture provided by Lightmol, some general information and links to other databases. And here is the list of interactions. So for each membrane, we store the data from the method, the charge and temperature for the experiment or simulation, and then we look into the individual parameters which we can obtain from that simulation or from that experiment. So, and then we can compare those data against each other. So you can see the caffeine is really a popular compound. Well, it makes sense since it's Friday coffee. So we can look also what else is in the database. And else we have transporters. And here for caffeine, we have the information about ABCC2, C3, and C4 transporters. And you can combine a look into the individual informations about whether it's inhibitor, substrate, and so on, and the individual values which are taken from the literature. And finally, here are the free energy profiles. So for instance, you can compare free energy profile from different membranes and different, so like this kind, you can see that the DOPC and DMPC membranes, which are both cell-like membrane models, have basically the same profile, while the stratum corneum mixture type membrane is quite different, and that makes sense because our skin is different than the rest of our cells in case of permeabilities. So these all these data are freely available. You can download them, export them. You can look into them at a web comparator. But of course, it's useful to work on your own as well. So let's move on to the presentation. So how can we actually, how many compounds and interactions do we have in the database? Currently, we have almost 500,000 compounds stored and approximately 1 million interactions that you can play with. They are all taken from approximately 1,500 publications, and we have approximately 50 different theoretical experimental methods. We have also data for about transporters, and we have approximately 40 plus membrane types. And here is what the comparator can show you is that you can basically compare what data is there for two different methods and to compare them along the different compounds, and to see that this experimental black lipid membrane model is with some relatively good correlation comparable to the computational model of pair MM by Lomiza et al. So what you can do with that, and that's the part where we actually started this story, and that was that we were interested in the metabolism of cytochrome P450s and the drugs by these. And when I came to the Palacký University, my first task was to build a model of these incredible enzyme bound to the membrane. And well, I built a model, and then we started to be interested into how the molecules interact with this protein, where the active site is so deeply buried inside the structure. So we found out with our another tool, MOL, which will be for another Friday coffee, we found out that there are multiple different channels leading into the active site or from the active site. And we started to wonder whether this will be somehow interesting for whether there will be some difference between the access channels and the egress channels. And we found it that based on where the molecules reside, we found that the drugs are usually more deeply in the membrane. Here is a guy which is quite often used these days. This is ibuprofen. And this guy is sucked into the active site by the access tunnel from the membrane. And then its metabolite is then egressed from the membrane, basically. Therefore, the cytochrome P450s are cleaning the membrane from this. So this is the start of the story, and we started to collect the data on membranes and metabolites and so on to see what will be the different effects of different metabolite or different metabolism. And here again, we can look into the caffeine. And the caffeine by itself, as I've already shown to you on live, is actually quite permeable through the membrane. But its metabolites are not, because as I've shown previously, the metabolites are less interacting with the membrane. So, but how much less? The demethylation increases the barrier. So you can get these three major guys, paraxanthine, theophylline, and theobromine. But if you add the oxidation actually has a higher effect than the demethylation itself. So trimethyluric acid is even less permeable than the demethylated versions of caffeine. And if you add also the dicyclization, you even increase. So this is the least permeable compound out from the metabolites of these cytochrome P450s or of the caffeine, and that's this 6-amino 5N-formylmethyl amino 1,3-dimethyluric uracil. So this is one way how this can be used, but in any case, it can be used also for comparison and benchmarking of different experimental methods and computational methods against the data. So it actually makes it easier to find the data for comparison. And currently, we are adding also the data on transporters into the field, so we can be able to compare between the passive and active transports. And we really wanted to make this thing as open as possible. So we ran on GitHub, and if you want to contact us, you can contact either directly me or contact us via GitHub. And if you would have any data that fits, we would love to add them. So let me thank to all of my collaborators on this, especially my students and my colleagues. And I thank you for your attention. And I've seen there starts to be the first question in the chat, but please do ask them more.
Thank you very much for a very nice introduction into that resource. And certainly we have a few questions already, so I can repeat them. Marian Novotny is asking if he can filter data to get only experimental measured data or calculation.
Yes, you can. Basically, we are now preparing the easier download because we are rewriting the statistics module to get the better grip about what will be the different what data we actually have in the database. That will be live soon, and there first you can download complete database right now, and then after all make the filtering on your side, because doing the selection of 500,000 compounds takes time on web. But we will be providing soon this information directly, because there will be the statistics for the individual methods. So it will be possible to select the methods you are interested in, membranes you are interested in, and download only the data for them.
Okay, thank you. Vojta Spivak is actually asking another question. As far as I remember, there is some possible toxicity of potential drugs due to their embedding in a membrane and their kind of crystallization in the membrane. It definitely has some name, but I don't remember it. It's planned as another feature of the database. The toxicity, if I understand well.
Well, the toxicity itself is not will probably not be involved, because we are looking only into how the molecules interact with the membrane. So for this part, I can only say that right now we are going into the partitioning to the membrane, and this can be found in the database. So you can select the compounds according whether they partition into the membrane so much that they won't basically go out from the membrane again. Yeah.
Okay, so Marianne has another question. Is there any 3D structure of small molecules with membranes?
Marianne, can you specify it a little bit more about what you mean by 3D structures of small molecules with membranes? Right now, we provide the 3D molecule of the drug or of the compound itself, because we are showing it in light mode.
Yeah, I know, but maybe I think like rhodopsin, for example, has a lot of small molecules in membrane. So I was wondering whether you also get the structure about the interactions of the small molecules with membranes. If there are any, I have no idea. I would assume there might be some already. So you show kinetics data, but you know, I'm always interested in interactions. So I'm asking about 3D structures of the interactions.
We are currently not providing that, but that would be an interesting addition, I would say.
Okay, Karel, I have probably another question. Is there any similar resource which is actually dealing with the same subject? Is there any database or any repository of the molecules penetrating membrane or dedicated to the molecules which are interacting with membranes?
There is several databases which are dealing with the transport data. These are actually in the Campbell. They are the Guide to Pharmacology database. They are at the EUPHAR. So for transporters, there is several databases. But as far as I know, there is no such database for small molecules. Well, actually, yeah, there is one, but that database is called PER-MM and is run by the Andrei Lomize at University of Michigan, and he is providing his own model, and he's also providing experimental data for the molecules on which he built the implicit solvent model for which he calculates the permeations. And last time I've seen, there was something like 500 compounds.
Okay. So I think the last question is for the membranes. It looks like only eukaryotes are included. What about prokaryote specific membranes? Do you have any data or planning to add on these?
Well,
was asked.
yeah, I see the question. Well, right now we don't have data for that, but if you know about any source where I can find them, I would gladly add them to the database.
Okay. So I see no other question. So Kara, thank you very much again. And all of you'd be interested, please contact Kara directly. And we'll be really happy if you would find some time to give us feedback, which Anna just posted on the chat. So thank you very much and see you next Friday on the Elixir Friday Coffee. Have a nice day.
Enjoy. Bye.